Does it work for everyone at the end? Okay, I don't hear any objections, so I assume you hear me. Yeah, we asked for a bigger classroom, and this is what they gave us. Yes, okay. So today we're going to talk about a completely new topic. We're going to talk about symmetric encryption. And we're still not ready to talk about cryptocurrencies. So this session is mostly about communications and how to have secure communication. And then we will later on use this in the design of our cryptocurrency as well. So here's the scenario that I want you to consider. This is our scenario. Let's say that we have two different people. So let's say I have Alice and I also have Bob. And they want to communicate. But the problem is they can only communicate over an unsecured channel. So let's say over the internet. So I have Alice on this side, I have Bob on this side, and they have some way of communication. Let's say this is the internet, but it's not secure. And again, by not secure, I don't mean that someone can tamper with the messages. I just mean that someone else might be able to read the messages. So let's say I can have someone called Eve, who's an eavesdropper, and she can actually read anything that goes through this channel from Alice to Bob or from Bob to Alice. Okay, so this is not secure. And Eve is going to basically spy on them. Okay. Now, let's say that I have a particular message that I want to send. Let's say I'm Alice. I want to send a message M to Bob. And again, as usual, whenever I don't define the type of a variable, it's just a string. Okay, so it's just a sequence of zeros and ones. It's a message, and Alice wants to send this message M to Bob. Now, another notation that I will use throughout this course is that whenever I write something in red, I mean that it's a private thing that should not be leaked to anyone. And whenever I write something in blue, I mean that it's public. So M is definitely private. And our goal is to make sure that Bob finds the same M. But well, of course, I cannot just send M through this channel because then Eve will also see my message. So ideally, what I want to do is that I want to be able to encrypt this M. Let's say I encrypt it into something called E. And this is the encrypted message. And then I just send E to Bob. And of course, Eve also sees what this encrypted message E was. And then ideally, Bob should be able to decrypt this message. And Bob should be able to receive E, and after receiving E, somehow get M out of it. But I don't want Eve to be able to do the same thing. So now the problem is originally, I didn't have any kind of shared information between Alice and Bob. So whatever Alice is sending to Bob, Eve is also seeing it. And we're assuming that Eve can also do any kind of computation that Bob can do. So it seems like the problem is again impossible. We will see that it's actually not impossible. But to make it simpler, let's say that we can have some sort of a shared secret between Alice and Bob. And for these shared secrets, I'm going to call them keys. So here's what I want. I want to have a particular key. Let's say I have a key, and let's call it K. And this key is also just a string. Now, the idea is that only Alice and Bob know this key, and no one else knows it. So this is a secret that is only known to Alice and Bob, which is known by Alice and Bob. Okay. Now, based on this key, I want to have an encryption function that Alice can call to encrypt her message. So I want to say that Alice knows a function. And this function, I'm going to call it ENC for encrypt or encryption. And what this function does is that given a key K, it maps strings to strings. So basically, if you give it a key K and you also give it your message, it will give you an encryption of the message. And I'm assuming that Alice knows this because Alice is the party who wants to send the message, so she should be able to encrypt it. Now, on the other hand, I want Bob to also know how to decrypt. So I want to assume that Bob knows another function, let's call it DEC for decrypt, that also takes the same key, and it also takes the encrypted message and gives us the original message back. Okay. Now, this is called symmetric encryption, and we will see non-symmetric encryption later. But basically, we call it symmetric because both Alice and Bob are using the same key in this setting. If it doesn't make sense to you why this is important at this point, it doesn't matter. We will see it later. Okay, so what is the property that I definitely want to have? Well, I want to say that for any possible message that Alice might want to send, so for any message M, if I encrypt it and then I decrypt it, I should get the same message. That's a very simple property. So the result of decrypting using the key K of the encryption of the message using the same key should be the message. Okay. Now, if I want to use my color coding again, so this message was supposed to be private, but this part here, the encryption of the message, this is what we called E, and this was public. So everyone can see. Now, the question that we have to really answer here is about the key and also the functions, the encryption function and the decryption function. So which one of these things are public and which ones are private? Now, the first crypto systems, and again, when I say crypto, I mean cryptography, the first crypto systems that were designed generally assumed that the functions themselves are also some sort of a secret. So the idea was that only Alice knows what kind of algorithm she should run to encrypt, and only Bob knows what kind of algorithm he should run to decrypt. But that became really hard really soon, and people didn't like it at all, especially because what happens if someone else finds out your decryption algorithm? You have to create a completely new system for your encryption and decryption. So nowadays, the standard is that the functions themselves are actually going to be public. So everyone, we assume everyone knows how the encryption and the decryption works. The secret here is the K. So the key K is a secret. So let me do this. My eraser does not work as usual. I have to figure out how to work with Windows at some point, but okay. So I have a secret key now, which is only known by Alice and Bob, but these encryption and decryption functions, they're actually public, the functions themselves, not the key. Okay, so I want to just come up with a bunch of functions that look like this, that if the two sides have a shared key, they can use these functions. Now, this is probably one of the easiest lectures of this course. So I'm pretty sure you already know what kind of functions we can use. So let's say this is K, and this is K here, so both sides know K. I'm going to use what we call a one-time pad. And the idea of a one-time pad is that you want to send a message M, and you just take your message and you XOR it with the key K. Okay, and we're assuming that they have the same length, or we're assuming that the key is long enough so that it's longer than any message that I might want to send. Okay. The encryption of a message M using a key K is simply the result of XORing M and K. And I use this notation to show XOR. Okay. Now, what would the decryption look like? If in order to encrypt, I just XORed it with K, the decryption would be exactly the same as the encryption, right? So I'll just XOR it again and I'll get my original message back. So this is E. E was the result of encoding M using encrypting M using K. And then if I want to decrypt this same message E using the same key K, I just define this as E XOR K. And it's super easy to check that you have the properties that you wanted. So if I can consider what happens if I decrypt the result of the encryption of a message M. What is this? Well, this is the decryption of M XOR K. So this is just M XOR K twice. But these two cancel out. So it's just, okay, super easy. But what is the property that we actually want? So in this definition, I'm just saying that if you encrypt and then you decrypt, you get back the same message. But that doesn't give me any security, right? So maybe my encryption and decryption functions are just the identity functions. They don't change the message at all. That would also satisfy this definition. So I want to actually have some security in there as well. And the security that I want to have is based on what Eve can do. So Eve can see what the encrypted message E was. And generally what I want is to make sure that Eve can never find my original message M based on E, right? But I actually want an even stronger property. I want to say that Eve cannot find anything about the original message. So these are kind of different. It's a much weaker security property if I say that Eve cannot find M. But what I want to say is that Eve cannot even find one bit of M. Eve cannot find any kind of information about M. Or another way of saying this is that if I have two different messages, let's say I have M and M prime, and I send them using this encryption, I send one of them using this encryption scheme. There should be no way for Eve to distinguish between the two messages. For any two messages, they should be indistinguishable from the point of view of Eve. So in my definition, I want to now add a security property. And the security property is this. It is impossible to find any information about the secret message M if you have, well, if you have the encrypted message E, but not the key K. So, of course, if you have the key K, you can just run the decryption process and you can get back your message M. But the idea here is that if you don't have the key, you should not be able to find any information. Okay. So let's actually verify this. And let's see if our one-time pad has this property. So again, here I'm just assuming that K was a secret key that was shared between both Alice and Bob. And I'm not really talking about how they came to share this. I'm just assuming that they had it at the beginning. But later on, we will talk about how to actually create this key. Okay. But now I want to do a small security analysis. So how do I show that it's impossible for Eve to find any information about them? Let's say that this string K, the key, was chosen uniformly at random. Okay. Then when I put myself into the shoes of Eve, what happens? So I can just see E, right? So Eve sees E. And what do I know? I know that this is the result of an encryption, and we assume that the encryption algorithm is public. So I know that the encryption was using XOR. I know the algorithm, I just don't know the key. Okay. So what are the options that I can have in my mind for the different messages that might be possible? So let's say that I see this E, and let's say that the length of E is n. So I have n bits in the encrypted message. Now, I also know that the original message had n bits. I don't consider that as a leak of information. I think like the length of the message is known. That's fine. But can I really distinguish between any of the 2 to the power of n possible messages of length n? No, because for every message of length n, there is a key such that if I encrypt it using that key, I will get this encrypted message, right? So this is the property that we have for every possible message that is of this length n. There exists a particular key, I'm going to call it Km, also of the same length, such that if I encrypt that message using that key, I get this encrypted message. Okay. So what is Km? Can you tell me what Km should be here? Yes. So if I just take M XOR E. Right? So here's the thing. The idea is that I don't know what the secret key was. I'm Eve. I just know that the encrypted message was E. So I just want to guess what the original message M was, and I want to narrow down. So if I can even rule out one possible message, that's some information that I have found about the original message, and that's not allowed. I should not be able to rule out anything. So now I'm saying that if I just see the encrypted message, the original message could have been anything. Because for any M that you give me, if it just happens that the key is this value, M XOR E, then the encryption of M would be the E that I'm seeing. So based on the E value that I'm seeing, I cannot find any information about what the original M was, because every M is possible. Okay? And just to check this, just to check that the formula works, if I define K to be that, then what is the result of encrypting M using K? Well, it's just M XOR with the key. But based on this definition, it's M XORed with M XORed with E, but these two cancel out. So the M actually canceled out, and I'm getting E in any case. So for every M, it's possible to encrypt it using a particular key so that I get the same encrypted message that I'm seeing right now. Okay. So this proves that I have kind of a perfect security, perfect secrecy here. There is no way for Eve to find out what the message was, or to find out any information on the message. Okay. But now we have another point here, and the point is this analysis worked only when I wanted to send one message. And that's actually why we call it a one-time path. So what happens if I send two messages? Yes. So that's actually a big problem. You should not reuse your keys here. So do not reuse the keys. Because if you send two messages using the same key, what happens? Well, let's say I first want to send the message M1, and then I want to send the message M2. Okay. Again, this side is Alice. This side is Bob. So when I want to send M1, I actually encrypt it. So what I'm sending here, which becomes public, is M1 XORed with K. And when I send M2, what I'm actually sending is M2 XORed with K. I'm using the same key, right? And actually, Eve can intercept all of these things. So Eve sees both of these numbers. So as Eve, I can just take these two numbers that I saw, or take these two strings that I saw. Anyway, in this course, I always say numbers, strings, these are all the same. They're sequences of zeros and ones. So I can take these two strings that I saw, and I can just XOR them. So Eve can compute the XOR of these two things. Let's give them a name. So I call this one E1, and I call this one E2. So Eve computes E1 XOR with E2. Now, what does this give me? E1 XOR with E2 is basically M1 XORed with K, XORed with M2, XORed with K. But now the two Ks cancel out. So what I'm getting is just M1 XORed with M2. Now, very important, I'm not really finding the two messages, M1 and M2. So I'm not violating the weak security property that I had before, which said that Eve should not be able to find the messages. But I'm actually finding some information about the messages. I know that the two messages had a particular XOR. I know the XOR of these two messages. So now I can rule out a lot of possibilities, right? So if I know, for example, that the XOR of two messages were 1, I know that it's impossible that both of my messages were 0. So if I can rule out some possibilities, that means I've gained some information about the messages. And that's enough for this to be not so secure. Okay. And then you can, of course, think about what kinds of experimental approaches we can have here. So if M1 and M2 are somehow sentences in English, and you have the XOR of two sentences, or even worse, if you have many sentences and then you can take the XOR of any two of them, then you can probably find some approaches to find more information and actually decode them. But okay, as far as we are concerned, just having the XOR is considered a leak of information, and this is not acceptable. So we cannot reuse the keys. Okay. But the other point that I made before, but I want to just emphasize one more time, is that only the keys matter. And we will see this in the other crypto systems as well. So I'm not hiding how I do the encryption and the decryption. I just assume that the attacker knows what kind of algorithm I'm going to use. It's just that I have these secret keys that no one else knows about. Okay. Now, of course, the next problem is, how do we have these shared keys? So let's say that I want to read my email from Gmail, for example. And let's say they're using this. They're not using this, but let's say they are. Well, I need to have a shared key at the beginning before they can even send me anything. Now, a naive idea would be to say, just use your password as the key. But then the problem with that is we cannot reuse our keys. So I can use my password for only one message. I have to actually find a way to create a shared key when there is no shared key. And that's what we call a key exchange. Okay, so. Now, what is a key exchange? A key exchange is that I'm in exactly the same scenario as before. So let's say I have Alice again on this side, and I have Bob on this side. And let's say Alice has a message M that she wants to send to Bob. Okay. but the problem is they don't really share any key. And they don't have any other way to communicate. So they can only communicate using this unsafe channel. Let's say this is the internet, which is not secured. They're using HTTP, let's say. And yeah, we have an attacker, Eve, who's intercepting this. So we want to somehow create a value that both Alice and Bob know, but Eve cannot know, using just messaging on this very unsafe internet. Okay. Now, again, this seems impossible because anything that Alice sends to Bob is also intercepted by Eve. And anything that Bob sends to Alice is also known by Eve. So how is it that I can somehow magically create something that both Alice and Bob know, but Eve does not? So the idea here is actually very elegant. And we're going to use a hard problem. So the idea is that I'm going to let Alice have a secret, and I'm going to let Bob also have a secret. Okay. So let's say that Alice has a secret A, and let's say that Bob has a secret B. Now, if they try to send their secret across the channel to the other side, then Eve will also know that secret. So we will definitely not send our secret. But what we can do is that we can apply some function to our secret and send the result to the other side. Okay. So maybe, let's say I have a function f, and this is my first step. I say that Alice computes f of a and sends it to Bob. Now, the reason for this is, again, because I cannot send A itself, but I want to send something. So let's just call that f of A. So I'm sending f of A to Bob, and now Bob knows f of A. But the problem is, of course, that Eve also knows f of A. Now, let's say that Bob does the same thing. So Bob also applies the same function f to his secret B and sends it to Alice. So he computes f of B and sends this f of B to Alice. Okay, now this is f of B. And Eve also knows f of B. Okay. Now you see, at the beginning, we started with a case where everyone basically had no knowledge except for their own secrets. But now if you look at the knowledges of the different parties here, it's kind of different. So Eve knows f of A and f of B. Alice knows A and f of B. Bob knows B and f of A. So I want to somehow come up with a computational problem such that if you have A and f of B, you can compute it easily. And also, if you have B and f of A, you should be able to compute the result easily. But it should be basically impossible to compute the same result using f of A and f of B. Okay? So this is the goal. We say we define our secret K. So define K, and I write it with this color because it's a secret, to be a value that is easy to compute by both Alice and Bob, but impossible to compute by Eve. I want a value such that it can be computed easily if you know A and f of B. So is easy to compute given A and f of B or B and f of A. So I want to say that both Alice and Bob can compute this value. But at the same time, I want it to be basically impossible to compute if you only have the f values using f of a and f of p. Now, if I can somehow design something like this is what I will call a key exchange protocol. Then I have a very nice property here, because at this point, Alice has a and f of b, so she can just compute the value of k. And Bob also has b and f of a, so he can compute the value of k. But we said that it's impossible to compute the value using only the f values, so Eve cannot compute it. So at this point, I will have a key that is shared by Alice and Bob, but Eve cannot have it, so I can just use this key as my one-time pad and just send a message now. Okay? But again, I'm not yet telling you what these f functions are. This is actually not too hard to come up with, but we will see several examples of them. I just want you to see the overall idea here. So I want to make sure that, first of all, I don't send the secrets through this channel. So this f is somehow a function that is masking my secrets. Okay, this is actually the role that hash functions had before, but we're not going to use a hash function here. But the idea is that I want to send some information about A, and that's called f of A. But I want to make sure that no one can find anything about A based on its f value, right? No one can find A based on its f value. And the same thing happens with B. So I have a secret B here. I don't want to send the secret itself. I just want to send a masked version of my secret. And then I want to have a final secret K. And the idea is that this K should be easy to compute if you have one of the two secrets, if you have A or B. And of course, the F of the other secret, which everyone has. But it should be impossible to compute if you don't have any of the original secrets. So this is what we want to design. Okay. Now I'm going to give you the first design of this, and this is actually called the Diffie-Hellman Merkle algorithm. And this is the same Merkle as Merkle trees. But actually, most people just call it Diffie-Hellman. So yeah, DH key exchange. I want to, first of all, use prime numbers here. So this is how I do Diffie-Hellman. So first, I want both sides to just choose a very large prime number P. Okay, this is my first step. And when I say I want both sides to choose, I mean, I don't care who chooses it. You can have Alice choose it or Bob choose it. I don't really care. So let's say Alice or Bob chooses a large prime number P. And I wrote the P in blue because this is going to be public. So they choose a prime number P and they send it to the other side and send it over. So now Eve knows my prime number as well. Now the idea is that instead of just working with bits, I want to work with numbers modulo P. So I want to work with the remainders of my numbers when divided by P. And when I say I want a large prime number, what I mean by that is that my prime number should be large enough so that it's larger than any message that I might want to send when I look at my message as a number. Okay, so any binary sequence is also a binary number. So just choose a prime number that is much larger than any message that you might ever want to send. And that's it. Okay. We're also going to choose something else. And this is a little bit of number theory, so just bear with me. We don't just choose a prime number P. We also choose another number called G. Okay. And this G is just a number that is between 0 to P minus 1. So generally, again, from now on, whenever I talk about numbers, they're numbers between 0 and p-1, because I always just take the remainder modulo p. Okay, but I want to find a number such that it has this very nice property that I will use later. I want to say that if I look at all the powers of this number g, so if I look at the set of all the powers, g to the power of 0, g to the power of 1, g to the power of 2, and so on, all the way to g to the power of p-2, this should give me all the possible remainders. So this should give me 1, 2 to p-1. Okay, that's what I mean. So basically, I want to have a number g so that if I start with 1 and I just keep multiplying g, I will get all the possible remainders modulo p. Okay. And the reason I call it g is because it's a generator, in a sense, like if you've seen group theory, it's generating all the remainders modulo p. Okay. And actually finding this p and g is quite easy. So I'm not going to get into that, but well, you want a large prime number. There are infinitely many prime numbers, so you can always find a prime number that is large enough for you. And actually, it turns out that finding g is also quite easy. So just agree that Alice and Bob can find p and g like this. And they sent both of them over. So both p and g are going to be public. So in here, I'm just going to say that Alice sends it to Bob. It can be the other way around. I don't care. P and G. Okay. Now we need to choose our secrets. Okay. So I say Alice chooses a secret. And Alice's secret was supposed to be called A. So I'm going to call it A, and this is a secret, only Alice knows it, so it's red. Now I said that I want to do all of my calculations modulo p. So yeah, the secret is also going to be a number modulo p. So Alice chooses a secret that is either 0 or 1 or so on up until p-1. And now I don't really care how Alice chooses this, but let's say she chooses uniformly at random. She just takes a random number generator, takes a random number, and then computes it modulo p and says, this is my secret A. Now, Bob does the same thing. Bob chooses another secret, a secret, and Bob's secret is supposed to be called B now in 0 to p-1. And again, all of this is because I want to have a key exchange like here. I want to have a situation where each of them have a secret at the beginning. And I'm saying, how can you have a secret? Well, the easiest way to have a secret is to just find a random number between 0 and p-1, right? And don't tell it to anyone. That's a secret. Okay. Now I know that Alice should send something to Bob, but she should not send the secret itself. She should send a function of the secret to Bob. That's the function f that we have. So here's where I'm using my number g. I'm just going to say, instead of sending a, compute g to the power of a and send that over. Okay, so this is my third step. Alice computes, let's call this one, well, I don't need to give it a name. Let's just write it like this, g to the power of a, and sends this over the channel and sends it to Bob. And Bob does the same thing. So it's very symmetrical. Whatever Alice does, Bob does the same thing. So Bob computes g to the power of b and sends it. Okay, so basically our hiding function f is to take our number g and raise it to the power of our secret. And again, as I'm repeating a million times here, all the calculations are modulo P. So when I say I send G to the power of A, I'm actually sending the remainder of the division of G to the power of A by P. Okay, so this is G to the power of A modulo P. I might not write modulo P all the time, but everything is modulo P. Okay, so let's look at the situation here. I'm going to write it down here. So Alice had A, Bob had B, and then Alice sent P and G. So Alice knows P and G, Bob knows P and G, Eve knows P and G, right? Then Alice computed G to the power of A and sent that. So instead of F of A, I now have G to the power of A, which is what Alice sent to Bob. And Bob sent G to the power of B back to Alice. And this is F of B, and this is also something that Eve knows. Now, this is getting kind of complicated, but you understand the point. Now, Bob knows G to the power of A, and he also knows B. So he can just take G to the power of A, and he can raise it to the power of B, so that he gets G to the power of AB. Right? On the other hand, Alice knows G to the power of B. So she also knows the secret A. She can, again, take G to the power of B, and she can raise it to the power of A, and that also gives her G to the power of AB. Right? So that's what my secret is going to be. My secret K is going to be G to the power of AB. Okay? And this is my fourth step. I say that Alice computes the secret. So my secret K is defined as, okay, she has G to the power of B because Bob sent it to her. So she takes G to the power of B. And she also has A because A was her own secret. So she can just raise it to the power of A. And that gives her G to the power of AB, which is our secret K. Now, Bob can also do a very similar computation. So he wants to compute the same K. The difference is that he has G to the power of A. This is what Alice has given him. So he takes it and he raises it to the power of B, because B is Bob's own secret. So Bob knows this, Bob can do this. And again, he gets the same thing. He gets G to the power of AB. So now I have a secret value, G to the power of AB, that is shared between Alice and Bob. Now, of course, the question here is whether Eve can compute it. So let's see what Eve knows. Okay. So Eve knows what information? So again, I always assume that everyone knows about the algorithms. So I'm not going to write that as part of the information for Eve. So Eve knows what our algorithm is. But other than that, she knows P and G because these were numbers that were leaked, basically. Alice sent them to Bob or Bob sent them to Alice. So these are public. So Eve knows P and G. Actually, I was supposed to use blue for this. What else does she know? Well, anything that Alice or Bob sent. Alice sent G to the power of A, and Bob sent G to the power of B. So Eve knows G to the power of A, and she also knows G to the power of B. Now, but what does she need to compute? She needs to compute K. Okay, so needs to compute K, which is G to the power of AB. Okay. Now you see the problem, right? If I don't have either A or B, and I just have G to the power of A and G to the power of B, how can I compute G to the power of AB? It's actually quite hard. If you could maybe obtain A from G to the power of A, if you could somehow compute what we call a discrete logarithm, then you could do this, right? But actually, discrete logarithms are one of the unsolved problems in computer science, so no one knows how to do it. And also, generally, no one knows how to compute G to the power of AB given this information. So now we are getting to a security analysis that is not very satisfying, but works in practice. And this is the security analysis. No one knows how to do this, so we assume it's safe. A lot of people have tried for a long time. No one knows how to compute K given that information. We don't have any proof that it's impossible. We just know that no one knows. And if someone can figure this out, they will probably become a billionaire, so they will not hack your email, so you can be safe. So yeah, I'm sorry about this part. It's very unsatisfying the first time that you see it, because there is no mathematical proof that this is impossible. It's just that, as I said, given this information, no one knows how to find this information. So if somehow your eavesdropper Eve is able to do this, then she has solved one of the long-standing unsolved problems in all of computer science. This is, in a sense, similar to when you prove that a problem is NP-hard. So no one knows if P and NP are the same. So when you prove that a problem is NP-hard, you're not actually proving that there is no polynomial time algorithm. You're just proving that no one knows a polynomial time algorithm until now. So we are in a similar situation. I don't know if it's possible to actually compute K given that information. Maybe there is an algorithm, mathematically speaking, but no one knows it. So this is safe as of today. And this is called Diffie-Hellman key exchange. And it's a way of ensuring that both parties, both Alice and Bob, have a key K in common that cannot be computed by Eve. And then if you have this key, then you can do whatever you want with it, right? You can just use it as a seed for a random number generator, and you can take the random numbers that come out of that random number generator and use them as the keys for your one-time pad. So you don't even need to do key exchange every time that you want to send a message, right? So if you just use this G to the power of AB as your key in the one-time pad, then you need to do a key exchange every time you want to send another message, because you cannot reuse the same key. But instead, what you can do is that you can just give this K to your C++ compiler as the seed of its pseudo-random number generator, and you can take the random numbers that it generates, and, well, they're not really random, they're pseudo-random and deterministic, and then you can use those as your keys for the one-time pads. Okay, that's it for this session. I'll see you soon.